Okay, so we are live. Hello, everyone, and welcome to MAE 209. And I don't know if I see some people's in the chat, so hello to everyone. Lecture 21, and I can already anticipate what some of the questions is going to be. Yes, we did lecture 20 after we had our midterm 2 on Thursday, and it was in person. It's good to see everyone's faces. And what we're going to do is I have to post the grades through Moodle. So yes, you will get your grades. It will be a little bit difficult, though, returning the papers, so we'll have to figure out some sort of time if you want to pick it up in person. So I'll send either an email or post it on Moodle to talk about that. About if you want to pick it up sooner. Otherwise, I'll have it the next time that we have an in-person quiz. Does that make sense? Oops. I'll just double check. Okay, so yes, what I'll do is I'll say the midterm 2 marks. Posted in Moodle Gradebook. And the lecture notes for lecture 20 are posted also on Moodle. Okay. Oh. I see. Of course, Moodle is down while we're trying to have our lecture. Okay. Well, just one moment. Oh, again, like marks and stuff like that. I will post I can post the average with it when I make my remark about the test on Moodle's site, just for privacy. Give me one moment. Oh, an RMC email too. Okay, because I was just gonna run and grab my phone and send a email to everyone. Well, interesting. Okay, well, unfortunately, I'd like to still cover this material today, and it'll still be recorded, and the link will be provided on Moodle. So let X and Y we'll say jointly distributed. Random variables with PDF f of x and y so then let's talk about the expected value then. So the expected value, let's say now we had marginal distributions. So we can write it in terms of marginal distributions. So I'm going to write it mu subscript x, and that's a capital X for the random variable, is equal to, and we integrate over the entire real line, so it's minus infinity to infinity, x, and it's the marginal times the marginal function of x dx, or if you prefer, we can, this is the, again, I was saying it, but that's the marginal Pdf of x, and we can write that out in full then, minus infinity to infinity, and we'll have minus infinity to infinity times, and if we are going to integrate, we'll do just that joint distribution, dx dy. Okay. So I'm not sure if it's in the textbook. The textbook was a little sparse when it came to details about something like this. So again, just make a note of this. I don't know if they explicitly defined it or not. And the other one that we can do is we can also do the expected value for y, and similar idea. So instead of integrating x, we're going to use y, and instead of using the marginal PDF of x, we're going to use the marginal PDF of y. Okay, so maybe I'll put that also in a box too, because so let's do an example. So I have my expected values there. So continuing the example that we had done in class from the previous lecture, and for those that are looking for lecture 20, this is the joint PDF that we were looking at. So we have the joint PDF. So it'll be 2e to the minus x, e to the minus 2y, and this is for values where x is positive and y is positive, and the PDF is 0 otherwise. So the expected values are separate? Yes. So this would be the expected value for x, and that would be the expected value for y. Yes, so these are two separate things. So hopefully that answered that question in the chat. So for part A, it's find mu of x. So to do this, we'll do this in two parts. Again, I need to find the marginal PDF first, and then I'll calculate the expected value. So again, those are kind of like my steps. I have to find the marginal and then calculate that. Okay, so when we calculate the marginal PDF, what we're going to do is we're going to integrate along the y-axis, and that will give us a function in terms of x. So if we integrate the joint PDF, and we're going to integrate this along y, that will give us a function in terms of x. And in this case, our function is defined when we have x is greater than 0 and y is greater than 0, and it's 0 otherwise. So we just need to integrate along the positive values. So I don't have to worry about the negative infinity. I just need to go from 0 to positive infinity. And I just copy down our joint distribution. Integrating along dy. And with this, then I don't have to worry about this 2e to the minus x. That can come out in front of the integral. So then we just have to integrate e to the minus 2y. And we've done that so many times that you can use a substitution, and what you would get is minus 1/2 e to the 2 minus 2y, and that's from 0 to infinity. Next, we substitute in our values. So if I substitute in infinity into this, this makes it go to infinity, and so this term goes to 0, so I don't have to worry about that. So I have 0, and then I'll have a minus, and a minus will give me a positive. And substituting 0 into the minus 2y, that gives me e to the 0, which is 1, so that leaves me with 1/2. And so those 2's cancel, and I'm left with e to the minus x. Okay, so then I can actually put this into my formula for the expected value of x. So I have x times the marginal. Now notice that this is in terms of x, and I'll have the marginal times x, and I'm going to be integrating with respect to x. So I don't have to worry about from minus infinity. I just need to go from 0 to infinity, again, because it's positive in this case. So this is a integral that we've seen time and time again, and so you can solve that using integration by parts. So if you do solve that, what you get is minus x plus 1 e to the minus x, and we're integrating from 0 to infinity. If I substitute the infinity in here, what I get is 0, so then the whole term goes to 0. And then the only thing I have to worry about is the minus. So I'll have a minus, and minus will be positive. Substituting that in here, I get 0. So that term goes to is 1. I'll have 0 here, so 0 plus 1 is just 1. So it's positive 1. So if we do it for, we can also do it similarly for u of y. And so we have to find the marginal of y. So I'm just going to just move this up here so that I have both the formula and the PDF, the joint PDF. So I need to find, so in this case, I need to integrate that joint PDF with respect to x. I want to get rid of x and write it just in terms of y. So again, and I'm just going to, in the next line, I'm going to write from 0 to infinity instead of the minus infinity. The other thing I can do is I can bring out in front the 2 and the e to the minus 2y. Because I'm integrating with respect to x, it doesn't depend on y, so I can pull that out in front from 0 to infinity of e to the minus x dx. And using, I suppose you can use substitution, would give you minus e to the minus x from 0 to infinity and substituting in the infinity, that goes to 0, and putting 0 into here gives you 1, so it's positive 1. So what I'm left with is 2e to the minus 2y. And then what's kind of cool about this is that this function doesn't, because again we're integrating, but we're integrating with a definite integral. I don't have to worry about a constant of integration. Because this is not an indefinite, it's a definite integral. Then, so for step 2, I need to integrate with respect to y, because now I have a function of y. So it's y times the marginal of y dy. And we'll be integrating from 0 to infinity y times. So again, make sure you pay attention to the intervals where the probability is non-zero. That will help you. Now substituting in our marginal. And you can use integration by parts, and I think you might also need a substitution in here. And what you get is a minus 1/2 e to the minus 2y times 2y plus 1. And again, that would be from 0 to infinity. And substituting in our values, well, if you put in the infinity into here, this makes it go to 0, so the whole term goes to 0. And also if I put in 0, this goes to 1, this goes to 1, and so I'm left with the 1/2. I have a negative, but my first term was 0, so I'll have minus will give me the positive 1/2. Okay. So that's the end of that example for the time being. We'll keep using that example for all the formulas in this section. So we can also have the covariance version. Of two joint continuous random variables. So the way that we will do this is we can go the integral from minus infinity to infinity. And again, I need to do a double integration. So minus infinity to infinity, integral of minus infinity to infinity. And I'll use x minus the expected value of x times y minus the expected value of y times the joint distribution, and the order doesn't matter in this case. You can change your orders of integration, however or whatever preference you prefer. But we'll write dx dy. So for our example, again, here's our joint distribution that we had before. 2 e to the minus x, e to the minus 2y for positive values, 0 otherwise. We also know what our mu of x is equal to. It's 1. And we had our mu of y is equal to 1/2. So what we can do then is put it into our formula. Okay, so what we'll do then, we have the covariance of x and y is equal to, and we'll have the from 0 to infinity for both of the integrals. We'll have x minus the expected value of x, which is 1, times, we'll use y minus 1/2 times 2 e to the minus x, e to the 2 minus y. And we can do this dx dy. And we just proceed by integrating this. we have a double integral, but there's some terms that are kind of not dependent on each of these x's. So what I'll do is I can actually break this integral up. So what I can do then is do 2, so I'll bring that out in front, the integral of 0 to x minus 1. And we have the e to the minus x, so we'll bring that here. And we'll do 0 to infinity of y minus a half, e to the minus 2y. And so we'll have to do the integral of dy of dx Now I have a question in the chat. Could I consider these as two separate integrals then? Because if I integrate this, this should give me a value, and then I'm integrating with dx. Am I able to write the following? Could I write it like this? So just in the chat, what do you think? Can I write it as these two integrals like that? Yes, okay. The reason why I'm able to do that again, because I can break those up into kind of these distinct parts. I have x in this part, and I have y in this part. So again, if I had integrated like this, again, this just gives me, just make sure you apply the dx to the resultant of dy. Okay. So everyone thinks I'm okay to do this. So what I'll do then is I will write it down. Okay, so to do this, what I'll do is you can do this using integration by parts. So again, this is a common one that I see over and over again. What I'm going to do then is just give you the integral. So that's minus x e to the minus x from 0 to infinity and if I integrate that, or sorry, I have integrated this, and now I have to use my values. E to the minus x to infinity, this goes to 0, so the whole term goes to 0. And also if I put 0 in for the second term, that goes to 0 as well. So what I end up having is 2 times 0 times the integral of 0 to infinity y minus a half dy, which is great because I'm multiplying by 0. I don't have to worry about this integral anymore because the whole thing has gone to 0. So is everyone checking my work? Is that okay? I'm just making sure if there's any objections. Any objections in the chat? Okay. Looks okay. So let's do another example, or I should. Okay, so we did the covariance. So the next thing I just want to mention is that we can have an arbitrary function. So for the expected value. So let's do the expected value. We'll use some of a function. We'll call it h of x, x and y. And that's a function. So if I do the expected value, let's say h of the random variables x and y, then, you know, we should compare that to what we're used to seeing. We're used to seeing for a continuous random variable that we integrate x times f of x dx. If we wanted to integrate that with h, so h is some function, that would be h of x, f of x dx. And that would also lead us to the special case where we consider the expected value of x squared. So again, we replace our h with the squared function, so that becomes x squared f of x dx. And remember that we're integrating over the entire real line, or there we go. So that's what we're used to seeing for the one variable. What does it do then for the 2 variable? Well, I'm going to replace this, instead of writing it with x, it's going to be x and y. So we have the function of x and y. Oops, and it should be little values. Right? I'm passing it in. Right? And those are the capital letters here. Try my best to distinguish my lower and upper cases. So we're going to integrate that, and we need to multiply it by the joint distribution. And instead of just dx, we have dx and dy, and we'll be integrating over from minus infinity to infinity for both of the variables. So again, this is something I should box. It's important. Okay. We need some sort of example. So let's use, here's an example. We'll let the random variable x be the amount of, let's say, amount of cashews, or almonds, sorry. We're going to do a mix of nuts. So amount of almonds, and y is the amount of cashews. In a 1 pound tin of mixed nuts. So how is this used differently from the separate expected values we saw earlier? Well, the other values that we were using was we were doing the expected value of x. And so in this case, I need to write this all in the form of x. So what I've done is I'm using a marginal PDF. And that marginal PDF is in terms of x. So I can integrate it very similar to how we did it with the 1 variable. So here's the 1 variable way. And again, we have x, and I need to have a function of 1 variable, and I do it with the marginal. Same thing with the y. I need to have a function of y, so I do that by using the marginal PDF. Now, this one is where I do the expected value of the function. So I have a function of x and y. So this is both variables. And what I'll do is the joint PDF follows f of x and y. We'll use 24xy. We'll say x is between 0 and 1. And this makes sense because we're working within 1 pound tin of mixed nuts. And y is going to be between 0 and 1. And the other condition that we need to be careful of is that if I add these both together, x plus y must be less than or equal to 1. and we'll have 0 otherwise. Now the reason for this is we're going to use less than 1 because there could be other nuts. So it's not just almonds and cashews. You can have Brazil nuts, you can have walnuts. So we're just looking at almonds and cashews, and they just have to be less than 1 pound altogether. So we'll use the less than or equal to. So the question is so we'll have if 1 pound of almonds costs, let's say $1. 1 pound of cashews costs $1.50. And they also then use 1 pound of peanuts. And those cost 50 cents. So this means that peanuts make up the rest of the mix. Well, what we would like to show then is, what is the expected cost? So in order to do that, here's our solution. If you want to think about it in steps, step 1, cost function. We need the cost function in order to figure out what the expected cost is then. So we need a function like h. So we'll call that h. I know you could put down as c, but just to make sure that everyone follows along, we'll use h. We'll use our random variables x and y. So for the almonds, it costs 1, because we're using x, we're going to use 1 times x, plus it costs $1.50 for the almonds, so 1.5 times y, plus 50 cents or 0.5 for the remaining. So again, there's 1 tin, it's a 1 pound tin, and then you want to subtract the amount of almonds and subtract the amount of cashews. And if we expand this out and collect like terms, what we're left then is with 0.5 plus 0.5x plus y. Make sure I'll try to keep all of that in this shot. Then step 2, expected cost. So what do we expect the expected cost of producing one of these 1 pound tin of mixed nuts? Then we do our expected value. So there's my function right there. So I'll need to go from let's put this in here. I'll have 0.5 plus 0.5x plus, and I got to be careful. I want to use lowercase letters because again, I'm using those values to integrate. So x, so a little x plus a little y, and it should have been 1, so there we go. Then we need to multiply it by our PDF, so our joint probability distribution. And in this case, it's 24 xy. And it depends on how you want to integrate this. So one way that we could do this is we want to integrate from, so we have x plus y. What I could do then is I could do y is less than 1 minus x. So that can be our condition. And that would be our condition on y. So we could go from 0 to 1 minus x. And because we're integrating, then that would be with respect to y. We'll have dy here. And over here, I would integrate from 0 to 1. This would be dx. And so you have actually a couple terms. You would have to expand this out. You might have, yes, so you would have, there's some work in there. And if you do that, what you get is $1.10. So there's some work involved. And so what this means is that, therefore, the expected cost of producing a 1 pound tin of mixed nuts, oops, is $1.10. Okay, so that's the end of that example. Is there any questions that we have before we sign off for today? My one question then would be, for next time, question, how do you calculate the expected value of x, y? Yes, that is the plan. The marks for midterm 2 will be on Moodle. Again, assuming that Moodle has not completely crashed. But yes, that is the plan. How many topics are remaining? That is a good question. We plan to cover some statistical methods in the last 2 weeks. And so depending on how much time we have left, probably around, about 4 topics in statistics. Just looking for the other sheet that I had. Okay, there we go. Okay. Well, if there's any further questions, feel free to send me an email at my RMC account once the RMC email starts working again. And again, I'll post these lecture notes on Moodle once it's working again. Thank you everyone for tuning in, and enjoy the rest of your afternoon. Take care, everyone.